Okay, last section, chapter 2, book 3.5, parametric surfaces. And we want to get surface area. That's our goal. We're working towards getting the surface area. And for instance, let's take a look at something like this. 2 parameters makes a surface. And we have u v 0.2u sine b over 3. That's a 3D object. And then it's given a values a range from u from -15 to 15. So this creates our domain of what we're allowed to put in for u and v to get a section of the surface. The surface would go on infinitely. You probably would expect that with this trig function here. And when we just focus on a section of it, the reason this is called a Gaudi surface is because the famous architect that has some beautiful work, like if you've ever visited Barcelona, just take a walk through there. It's amazing architecture. Anytime you see one of these crazy, bizarre buildings, one of them is the Sagrada Familia Cathedral. And the part of the roof of that, well, part of it kind of looks like if you're out on a beach and just dropping sand onto a sandcastle, has that sort of organic look. And then there's a back section called the Escolies that has this shape. So let's look at what that looks like as a surface. He's one of a few non-traditional architects that used parametric surfaces in their designs. Frank Gehry was another one. Okay, so we're back in CalPlot 3D. We selected a parametric surface. I've already entered this one, u v 0.2u sine b over 3. We want to go from -15 to 15, -25 to 25. And let's see, it looks sort of geometric there. So let's smooth it out a bit by adding some more grid curves, which makes the picture look more nonlinear and less partition geometric. So it has this form. And again, if you just Googled on the Sagrada Familia roof, you would see this in the back, this sort of undulations, wavy roof. And what we want to do now is get the surface area of this section. As usual, I think I've told you, you can go up here. I don't like seeing that box, or if you didn't want to see like the labels on the axes, but let's go ahead and keep those because we might need them later. And maybe let's turn it to a constant color. Let's go right, tone it down. Okay. Now, to get this surface area though, what we're going to do is something that we've done often. And in fact, you can kind of see it here in this tool, that each little section is like a little parallelogram, right? And we're actually going to use that idea that taking this nonlinear surface and dividing it into a bunch of little patches, little linear approximations. And I think your journals have a nice picture when we get the surface area. Yeah, a page on quilted approximations. Oh yeah, so there is our Escolies of the Gaudi surface on the Sagrada Familia, but there's a really nice other design in an oceanographic museum, I think also in Spain, that has this union of hyperbolic paraboloids, so that's a cool roof as well. But the idea that we're going to use here is that I have actually a nonlinear smooth surface, and I'm going to approximate it by getting a bunch of little patches of that are linear. So a bunch of little tangent planes that I'm going to stitch together and make what I've called here in this title page a quilted approximation. So we're actually going to take the nonlinearity, which is nice and smooth, and we're going to divide it into a bunch of flat patches that are linear. To do that though, to get those tangent planes, we need to figure out the normal vector at a particular point. So back on our Gaudi surface, at any point here, and so let's go ahead and add this section. You can add a point and move it around on the surface. Oops, over here. Move that point around and it'll display at the top what the u and v is and then what the x, y, z coordinates are on that particular point for our range, which was from -15 to 15, -25 to 25 along the y. I mean, this is u and v's, which then create x, y, z's. And I can move this blue point around. And of course, I'll have a different normal vector. Like when I'm down here in this little valley, let me see if I can get over there. Yeah, right along in there. we'd expect maybe a normal vector pointing out like that. If I'm up here on this ridge, pointing up, pointing over. So those normal vectors are going to change depending on where I'm at. And I need to figure out how to get those normal vectors to make the tangent plane. Now think back to, this was chapter 1, I believe. If I had 2 vectors, I could get a third one that's normal to those. But I just need 2 vectors in the tangent plane. So that's where we're going to start. How do I get those 2 vectors in the normal plane, in the tangent plane? Easy to then get the normal one with the which kind of product? The cross product. So if I could just get these 2 that live in the tangent plane, then I'm good. I can get the equation of the tangent plane. So we're going to start with that. How do we get those 2 that live in the tangent plane? Then we'll add up all these tangent planes and we'll get a surface area. So let's start by taking derivatives. So this is the first time we've taken a derivative of a parametric function of 2 variables. And so we could take, and these are called partials, and you'll have them with respect to x or with respect to u, with respect to u or with respect to v. You can take a partial with respect to u and a partial with respect to v. Just like you did partials back in book 3, this is going to be no problem. We will create a vector. So I look at the first component, take its derivative with respect to u, I get 1. Look at the second component, which is a v, take its derivative with respect to u. Or when u looks at it, you've got your u goggles on now. V is just a constant, so its derivative is 0. And same thing. Now the last piece, 0.2 u sine 2 divided by 3, v divided by 3. This sine v over 3 is just a constant, just like that 0.2 is. And so when I take the derivative, it's just going to be 0.2 sine v over 3. Now this partial can be evaluated at any u and v, and it'll spit out a vector. And that's actually what was happening when we were in CalcPlot3D. It'll spit out a vector at any one of those blue points that I move along the Gaudi surface. Every blue point has a u and v associated with it, and therefore it has a RU vector associated with it. We'll talk in a moment what this means geometrically. Let's do R of v for any uv. 0, 1. Now the v is inside the sign, but the 0.2 u is still just a constant, so that's going to get carried along, times the derivative of sine, which is minus cosine. I'm sorry, derivative of sine is positive cosine. V over 3 times the derivative of the angle v over 3 with respect to v, which is 1/3. All right, so now these are my partials u and v for any u and v. But let's say we were interested in a particular point. Let's just pick one here. Let's say when u equals 1 and v equals 2, let's say. I could compute u of 1, 2, and r of v, 1, 2, by just plugging into the partials I've already done. So r sub v, 1, 2 will be 1, 0, 0.2 sine 2/3. R of v will be 0, 1, 0.2 over 3 cosine of 2/3. All right, we could turn those into their decimal form if we'd like. Maybe we will before we put them into CalcPlot3D. So I want to show you one more thing before we share the screen and go back to CalcPlot3D, which is what is the point on the surface when u is 1 and v is 2. So how you get that is you plug in here. So r of 1, 2 is when u is 1, I get 1 in the first component, 2 in the second component, 0.2 sine of 2/3 in the third component. And that actually, even though it's a vector, it's also the terminal point of that vector, and that terminal point is an x, y, and z. Right? These are always x, y, and z components. This is a function that gives you an x in terms of u and v in general, a y in terms of u and v, and a z in terms of u and v. right? So let's go back to CalcPlot 3D and check out a few things so you can visualize what I've just said. Okay, so let's pick this blue point and make it the one that we had, which we ranged u from -15 to 15. So that's actually this axis, the x-axis here is the u-axis. And we want u to be 1. So we can go ahead and actually enter it right here. And then we want v to be 2. So that's actually where we are on the surface at this blue point. When u is 1, v is 2, that actually creates the point on the surface 1, 2, 0.2 sine 2/3, which is actually 1, 2, 0.12. So that last component is 0.12 if you turned it into a decimal. And those are given as an x, y, and z coordinate. Okay. And next thing I want to show you, because I need to run and get my charger, so I'm going to pause for a moment. Okay, so we were at the point 1, 2, 0.12 on the surface, which is also the same as u equals 1, v equals 2. That's this blue dot. And then we have our partials from that point. And so I want to input those vectors. So I selected vector, and I've already entered those. So the r sub u vector at the point 1, 2. So I'm starting from the blue point, which was 1, 2, 0.12. I entered that as my initial point. And then I want to go in the direction of the partial with respect to u, the r sub u vector. We'd already calculated that. That was 1, 0, 0.2 times sine of 2/3. So I just entered that in here. And I put that in red, put that vector in. And it's hard to see from this angle because it's such a short vector. So let's just actually, you can see the little red arrow there, but let's just magnify it by multiplying every component, let's say by 5. Doesn't change the direction, of course, it's just multiplying it by 5, it's lengthening it. Just so we can see, so there's our red partial with respect to u. And notice that that vector moves just like the grid curve there. And in this case, the grid curves are not so wavy at this point on the surface. Other point, they might be a little more bendy or nonlinear, but these ones move almost like the axes there. Let's do the same thing with the r sub v vector. So I've entered that here in green. Right now, again, it's very short. And that is the exact length of that vector, that derivative vector. We need to start at the blue point. So I changed the initial point to r of 1, 2, which is actually the terminal point of the vector 1, 2, 0.12. We already calculated that. And then our r sub v vector, we've calculated at the point 1, 2. We plugged in 1, 2 for u and v. We got 0, 1, 0.23 divided by 3 over cosine 2/3. So I've entered that in. And again, it's a very short vector, but just to see the length, let's maybe multiply that one by 5 as well. So I'm going to take each component, multiply by 5. And there's our green vector. That's the r sub v. The red one is the r sub u. Those move like the grid curves. In this case, they look perpendicular. They probably are nearly so at that point, but that's not in general, right? So if I was to move to a different point on the surface, that wouldn't be the case. Right? In general, they are not necessarily perpendicular. Look at a different surface, and there's a couple in your journal that you can take a look at for the circular parabola facing down. The two RU and RV are always tangent to your grid curves. That's true, but they may or may not be perpendicular. And so you can move this point around. Maybe you want to try u equals 10, u equals, let's say, 13, v equals 2, then you're already sort of on the edge of that roof over there. What would you have to do to get these two red and green vectors for the r sub u and r sub v, which we know should be tangent to the grid curve? So something like this and something like that. those two would be derived by just, you've done all the work, you just have to plug in r sub u at 13, 2, figure out what this vector is, r sub v at 13, 2, figure out what this vector changes to. And now we have two vectors that have to be in the tangent plane, right? Does that make sense to you that those red and green vectors, so going back to the original point we had, viewing this, those red and green vectors have to live in the tangent plane at that blue point because they are tangent to the grid curves there. Those grid curves both go through the blue point. So these are two vectors in a plane. I can take their cross product and get the normal vector then, which is the normal vector to the tangent plane that we desire, because we want to take a bunch of sections of tangent planes as we move all around, right? Tangent plane here, a tangent plane right next to it, a tangent plane there, a tangent plane. And we'll get the areas of each of those little sections of the tangent plane, add them up, and we'll have our surface area. Okay, so first concept that we need for this piece of the puzzle, derivatives. No problem, just like partials from before, we can evaluate those partials at a point. This time the visual is that these partials evaluated at a point give us directions. Those directions move in the direction of the grid curves. They're tangent to the grid curves. Now, and we know they're in the tangent plane. How do we get, if we had a little section of the tangent plane at a point, like for instance, we were at the point u equals 1, v equals 2, which also happened to be in XYZ, 1, 2.12, right? And we went in the direction of r sub u, in the direction of r sub v, and we formed a little tangent plane from the parallelogram formed by those. How would we get the area of this shaded region of that parallelogram? So this is going back to chapter 1. Remember what the length of RU cross RV is, right? So the length of the derivatives, when I compute these, I actually get r sub u cross r sub v. And the length of that represents the area of the parallelogram. So that was a fact going all the way back to chapter 1. And now we want to take those. So these are some pictures I think are going to be helpful here on the surface area page in your journals. Again, we're doing at a particular point, we're taking our two partials, getting the area of the shaded region, and that is just given by the length of the parallelogram formed by those two vectors. And then we want to sum those up. And so we would do it for like all these little sections, all these little patches of the surface, which are actually creating a quilt then. And so we want to get the area of that parallelogram, the area of that one, and that one. All of these little parallelograms whose areas are always given by lengths of cross product vectors, cross product of two vectors. Right, so we're going to take that, sum those up over the little parallelogram that was next to it. There might be another little one that's an approximation next to it, another one here. Sum those up, and we'll do that over all of them, and we'll eventually get to a double sum over a length. And then these are the small changes in the x, the u and v directions, which are eventually going to get us to a double integral. So doing the same process we always do, approximate, refine the approximations to exactitude, and we get a double integral. But before we can even get there, we need to get back to knowing about the tangent plane, these little sections of the tangent plane. Okay, so let's back up a page to our tangent plane page. And so the problem we want to work now, we have all the pieces of the puzzle. Let's go ahead and get the tangent plane. So for the Gaudy surface, let's do this. Again, we're not ready for surface area yet. Let's find the tangent plane for the Gaudy surface at the point u equals 1, v equals 2. Okay, well, we have all the pieces of the puzzle, and we had the picture from CalcPlot 3D. we had our two vectors, r sub u, r sub v. We've already computed those at the point 1, 2, these two here. We know that if we cross those two, we get this blue one is the normal vector. So we just have to do a cross product calculation here, and we'll have the equation in the normal vector. We have this formula, n dotted with x, y, z is equal n dotted with the point that you're interested in. This is actually going back to book 3 when we learned about tangent planes for explicit functions. Same thing holds here. So once we get the normal vector will be r sub u at 1, 2 cross r sub v at 1, 2. And so once we get that, the left side's easy. We'll just take those components, dot them with x, y, and z. And then we need r sub 0, the point that we're at. Well, we've already actually computed that up here. So when u equals 1, v equals 1, r sub 0 is really the point 1, 2, which was the terminal point of this vector 1, 2, which we calculated as 0.12. 0.12 was that 0.2 sine 2/3. Right? So that's what's going to go right here. And we have almost all the pieces of the puzzle then. So we just have to do a cross product calculation, maybe just to review it, and then we'll check it with Wolfram, which does that very easily. So the normal vector, we do I, j, k, 1, 0, 0.2 sine 2/3, 0, 1, 0.066 cosine 2/3. So we need to do this determinant, 2 by 2 determinant, and n will then have 3 components. Remove the first row and column, do the diagonal minus the anti-diagonal. So 0 minus this, so minus 0.2 sine 2/3 in the first component, comma, the second component, remove the second row and column, do the diagonal minus the anti-diagonal, and negate that. So negative 0.066 cosine of 2/3. Then the last one will be positive. I'll remove the last row and column, diagonal minus anti-diagonal, so I get a 1 in the last component. So the normal vector is given by this, which we can turn into a decimal form before we actually write the plane. So let's actually check that as well. From and they have a cross product calculator. We'll enter our vectors. The 2 vectors we were crossing were the 2 partials, r sub u at 1, 2, which was 1, 0, 0.2 times sine of 2/3, 6, and then r sub v at 1, 2 was 0, 1, 0.066 cosine of 0.6. Okay, so the cross product computes this decimal vector here. It's a 3D vector, which shows the plot, the 2 vectors that we input, and the third one being normal is the final one output in red. So the normal vector then, which we gave an exact form, also has approximate form. Let's just have a few decimal places here just for the sake of this example. 0.12 minus 0.12 minus 0.05 and 1. Okay. Right, now that normal vector is used in our usual tangent plane formula. So the normal vector will be minus 0.12x minus 0.05y plus z is equal to that normal vector. So a little more work. Normal vector dotted with r sub 0. It's going to be these 2 vectors in blue dotted, dot product So what is that? Minus 0.12, minus 0.10, plus 0.12, minus 0.10, and then that goes right here. This is the equation of the tangent plane at the point u equals 1, v equals 2, which is also the same as the point 1, 2, 0.12 in x, y, z. And you can check this, as this would be a good thing. Also in Calc-Plot 2D, 3D, we also we put the two vectors, the red and the green. We put RU in red, I think, RV in green. We put the point R0 in the blue dot. And now add one more vector from that point, R0, add the normal vector, add that in, and you'll see that goes directly perpendicular to those two. And then go ahead and enter this. You know how to enter a plane in Calc-Plot 3D at that point? Enter to make sure the plane goes through the blue point, and the plane is a linear approximation. The plane will extend, the further it extends, the worse the approximation gets. So just do a small little section of that plane. And this is a way to check another point we did last time, 13.2. That'd be another good one to check. Visually make sure you can get the r sub u in there at 13.2, the r sub v at 13.2, the normal vector at 13.2, the tangent plane that contains both of those at 13.2. Okay, so last bit, surface area. All right, so we're making this a long video, so I'm just going to try to quickly run through this last little section. We have all the pieces now that we have the tangent plane. We can go ahead and get the surface area. Let's actually do it for the Galby surface again. Let's now go back to the original problem. Find the surface area for the Galby function that lives all the way from minus 15 to 15, minus 25 to 25. We don't have to define it at a particular point now because we're not doing local approximations. Those local approximations, though, actually help you get to this next double integral. So we want to calculate the double integral of the magnitudes of r sub u cross r sub v, dv du. V goes from minus 25 to 25. U goes from minus 15 to 15. In this case, those are constant limits of integration. If it helps when we get further along, we could switch the u's and v's, the order of integration rate. R sub u and r sub v, those were your partial vectors. And so we would take double integral of these two vectors, get their magnitude. So we had, let's see, with respect to u, we had 1, 0, 0.2 sine v over 3. We need to take that general vector and cross it. We had crossed it with specific vectors at a point where we did now do this generally with the r sub, so this is the r sub u, with the r sub v, which will be 0, 1, 0.2 over 3 u cosine v over 3 magnitude dv du. Okay, now we have to do a cross product with general u's and v's in there. And there are cross product tools to do that. You know how to do it by hand. We can quickly do that and then show you the cross product. Then we have to get a magnitude. So let's share the screen. Go back to cross product calculator, and we want to enter ours, which is general now, 0.2 sine of 0.33b 0.066 times u times cosine 333 v and what you get now is a vector that has u's and v's in it. And now this result is a vector, and we can actually take that and ask to get the length of that vector. So we get the vector length, which again, some of the components squared, so not hard, it's just tedious. Right. Oh, actually, I don't need those. It already has these parentheses there, so let's try this. This will be a messy looking thing, which we expected. Sum of components squared. And then you could ask, finally, so that's what we go here. Another double integral, a square root, that messy thing, u to the u, same range, 25 to 25, minus 15, 15. And then you could ask to integrate that, this thing, from u equals minus 15 to 15, and b equals minus 25 to 25. Okay, so we get a value. It spits out a decimal approximation for us there, but that's the same steps of everything we've been doing so far in this class. We just finished the last part of book 3 was about doing these double integrals. Then they represented volume. Now when we take the square root of the two partials, we're actually getting areas of parallelograms, and then we're summing up the areas of those parallelograms as u and v get really tiny. So we're taking infinitely many parallelograms in our quilt. Our quilt is getting to be a very good approximation until it becomes exact. And you could just quickly check to see, just eyeballing this too, if this Gaudi surface has these nice undulations, but if it was just completely flat, it was just a plane, what would you expect that the surface area of that section of the plane would be? Well, it would be 50 units in one direction times 30 units in another. So 1500 would be our rough approximation for the guess. Let's go back to the surface. Right, so if this surface, you can see all the undulations there of the roof, and that's what makes it the cool part of the cathedral. If that were just a flat plane, the flat plane would have an area of 50 times 30 is 1500, and we just got with Wolfram slightly more than that, which is what we would expect. So that's a good eyeball check of what we're doing. Okay, so let me quickly summarize. Just making a long video here. This time we covered surface area. In order to get surface area with this exact method with a double integral, we had to build up some pieces of the puzzle. The first piece of the puzzle was derivatives. We could take a derivative with respect to u, which moved like a grid curve. We take a derivative with respect to v, which moved tangent to another grid curve. Those two had to live in the tangent plane. To get the equation of the tangent plane at any particular point, you take those two partials, cross them, get a normal vector. Now you have the normal vector to the plane. You can use stuff from book 3 to define the equation of that tangent plane, but you can also go back to your two partials and get their cross product, the length of that cross product. And the length of that cross product gives the area of a parallelogram at that particular tangent plane. We do a bunch of those together, sum them up, and we get an approximation to the surface area by doing this quilted idea. And then when we take those patches of the quilt to make them tiny, which is another way of saying take the number of patches and make that infinite, you get your double integral, which messy to do by hand, except for very basic, which you find out the by hand ones that are in textbooks are typically things that you could have done another way. Like, oh, it's really just a plane. It's really just a cylinder. So geometric objects, which are easy enough that make the algebra easy enough, aren't interesting enough on real problems, but real problems like a Gaudi surface, that Oceanographic Museum in Spain, Frank Gehry's, if you want a roof of one of his structures, you're going to be quickly getting into nasty things where you're going to need to use one of the numerical tools. So our focus here is on, can we model this? Do we actually understand what's happening? Can we model it? Okay, that's chapter 2. A lot of material, but a lot of neat stuff until we get on to one last cool chapter in this journal.